Hi everybody, it's Dr. Chris here. Today is Sunday, February 16th, and this is your snow day lecture. So what do I mean by that? Well, on Thursday, February 13th there was some snowstorm going on, so the afternoon class was canceled. So those of you who I saw at my 10:30 class will have seen most of this lecture, although I have made some changes and some improvements, and so it's worth watching again. Those of you who would have been in my 1:30 class, well, you would have missed this lecture, and so it's really important that you do watch it. So if you are watching that right now, well, I thank you. I'm glad you're doing it. So make yourself comfortable. Get out a calculator, have pencil and paper ready for the questions that I'm going to ask you. What I'm going to do this time is when I get to a point where I want you to answer a question, I'm just going to pause my own self and for a couple of seconds, and that pause will give you a moment to pause the video and to answer the question. It will also cue you in. It will tell you when it's time for you to pause the video. And so we'll do that. And what else do I want to say? I think that's it. Let's go and look at the next slide. So right, in this video, we're going to do basically two things. First, we're going to look at chi-square tests one more time. And here we're just going to look at a single example. And after that, the new stuff is going to be having a look at inferences for regression, some practice problems. Now, if you hadn't watched the baby lecture number 3 yet, which is also posted in the YouTube, then you should watch that before you watch this video. And I know for a fact, just because I can see the number of views I have on that video, that about 2/3 of you haven't watched baby lecture number 3 yet. So that lecture introduces new concepts for regression, and those new concepts are being practiced in this video. So if you haven't watched that video yet, baby lecture number 3, I highly recommend you go back and do that first and then watch this one. Having said that, let's move on. So here's our practice problem. So this is interesting because this is one of the cases where I'm actually using real data. It was a couple of years ago, around Christmas time, I went down to the drugstore and I bought a box of Lindor chocolates. And then I counted the number of each kind of chocolate. So we have, these are truffles, and we have milk chocolate truffles, dark chocolate, white chocolate, and hazelnut. So we have 4 different kinds of truffles. And I counted the number of each kind that was in the pack. And then I asked myself, could it be that in the factory where they manufacture these chocolates, could it be that these chocolates are manufactured in equal proportions? In other words, could it be that in the factory they make an equal number of milk chocolate, dark chocolate, white chocolate, and hazelnut? What are they called again? Truffles. Yeah, truffles. So do they come in equal numbers in the factory? And so how can we answer that question? Well, I have a sample, and based on the sample, I can make an inference. That's basically the idea. So the first question here is, what kind of chi-squared test should be conducted in order to answer the question that's being asked here? Right, so did you hear that? That was my pause. So that was my indication to you that if you want to, you could have paused the video, tried to answer the question yourself, and then continued. So what kind of chi-squared test is it? Well, here, it's a chi-squared goodness of fit test. And so let's remember what that scenario involves. So first, in this scenario, you're given a sample of counts across one categorical variable in a frequency table. And what do I mean by frequency table? I mean something like this. So here we have our 4 categories, our 4 types of truffles. We have our observed counts, and then on the bottom we have our total count. So this is our frequency table. Now, and what do we ask? We're asked whether these counts are consistent with a specified probability distribution. Right? In our case, the specified probability distribution is one for which each of these 4 categories occurs in equal proportions. And so those proportions would be 0.25 for each of the categories. So the null hypothesis here is that the sample counts are indeed consistent with the hypothesized distribution. And so here, to recognize a chi-square goodness of fit test, the most important thing is to identify how many categorical variables, you should see only one, and how many populations are there from which a sample was drawn. Here there's one population. In this case, the population would be the population of all chocolates, all of these truffles that are produced in the factory. the package that I bought represents a random sample from that factory. Okay, so one categorical variable and a sample drawn from one population. Oh, by the way, let me say this right now. I'm going to say it again later, but I've been told that on your midterm, which is going to be at the end of the first week you come back from reading week, so it's going to be on that Thursday, 27th of February. Let's see, chi-squared tests. Yeah, chi-squared tests are covered, but only goodness of fit tests. So that's good news because that should make it easier for you. So going through this example is sort of a bit of preparation for that midterm. Right, so the next question is, given that we're going to do a chi-squared goodness of fit test, I want you to write down the null and alternative hypotheses for this scenario. Okay, so hopefully you paused and you tried to write something down. There's more than one way to write down the hypotheses. You can write it in words. You could say the null hypothesis is that the observed counts are consistent with the proposed distribution. That's a very generic, general way of stating the null hypothesis. And so here in this table, you can see the proposed distribution would be each kind of truffle occurs, they all occur in equal proportions, so 0.25 each. Another way this null hypothesis could be presented, and you might very well see this on a midterm or final, or in the lab, and that's where you actually specify that the proportions are all equal to each other. So here, under the null, the proportion of milk chocolate is equal to the proportion of dark chocolate, is equal to the proportion of white chocolate, is equal to the proportion of hazelnut. All those proportions are equal to each other. So that's a way you can write it in symbols. The alternative is usually very simple to state because it just means not the null. And so in this scenario, if the null isn't true, that would mean that at least one of these four proportions is different from the rest. And so we could just say, yeah, at least one proportion is different. Just notice we have a spelling mistake there. So I just put an N in there, save, and back we go. So the alternative is at least one of these proportions is different. Okay, next question is, let's see if you can remember what are the conditions that are required to perform this chi-squared goodness of fit test. There's 4 of them. And maybe here you can just pause the video and maybe you can write it down, or you can just think in your head, count on your fingers what these 4 conditions are, just as a way of rehearsing them. Right, so as I've covered this in class, what I said is if you're doing a goodness of fit test, you have to have 4 conditions satisfied. First, you have to have one categorical variable. Next, you have to have a sample drawn from a single population. Third, it has to be a random sample that's supposed to give us independence. And then lastly, all of the expected counts have to be 5 or more. So this is the way I've been talking about the conditions. I noticed on one of your MyLab assignments for chi-square tests, they discuss the assumptions in a slightly different way. So I want to go over that just to make sure you're good with that. These are the conditions that they give. Now notice they separate the randomization from independence. And in my mind, that's actually a good thing to do because as I've said before, you might recall, randomization does not guarantee independence, and it's possible to have random data without independence. That is possible. So I'm going to just talk about a little bit about independence because it's probably the trickiest assumption. Anyway, let's see. So let's just go through the obvious ones. So in this scenario, which of these conditions are satisfied? We can start by saying we do have count data. And so condition D, count data condition, that's satisfied. And we also have a random sample. So we're assuming that this box of chocolates I purchased represents a random sample taken from the factory, taken from the population of these truffles. So we can say those 2 conditions are satisfied. That comes directly from the scenario. Next, we need to consider independence. Now this one is a little bit tricky. So independence in this scenario is satisfied if we can assume that the random sample was drawn from a large population. Now, the statement that I just read isn't always true. In some scenarios, this statement wouldn't guarantee independence. But in this particular scenario, it actually would ensure independence. Now I'm going to explain why that is. So I'm going to say independence is satisfied, but let me explain in a bit more detail. So here about the independence assumption. So independence in this context means that the probability distribution for the next truffle selected from the population of truffles in the factory is independent of what has been selected already. Okay, so let me just make this a bit more clear. So just imagine we're going to go into the factory. We have access to the entire population of truffles. We have our little bag. We're going to take at random 74 truffles. Now here's the point. The first truffle I pick, whatever that is, I put that in my bag. Then I pick a second truffle, whatever it is, I put it in my bag. And you can see I'm sampling without replacement. And as I said in class, probably more than once, if you sample without replacement, you're actually changing probabilities. So what I'll say here is we can assume we have independence. We can assume that the probability the probability distribution for the next truffle I select, that probability distribution is not changed by the truffles I've selected already. Right, and we can assume that's the case because the population of truffles is presumably very large. Okay, so let me make this a bit more concrete. So let me just read through this. So to see what I mean, suppose the population of truffles in the factory consists of 1,000 truffles. And suppose we have 250 of each type. And so in other words, let's suppose that the null hypothesis is true, that in the factory they make an equal number of each kind. Now we're taking a sample randomly and without replacement. So the probability that the first truffle selected is milk chocolate, for example, is 250 over 1,000, so it's 0.25. But the probability that the second truffle selected is chocolate, given that the first one was chocolate, it's now 249 over 999. Why? Because I already removed one chocolate truffle from the population. So now there's only 999 truffles in total left over, and 249 of them are the milk chocolate. So you see that the probability now, that the next one I pick is milk chocolate, that probability has changed a little bit. It's gone down a little bit. So technically speaking, the independence assumption is violated. However, the difference is also very small. And if the population of truffles is very, very large, let's say in the millions, like it's a big factory, there's millions of truffles, then even though we're sampling without replacement, that big population means that the differences, the changes in the probabilities are going to be so small that we can just ignore them completely. So hence, if we assume that the population of truffles made in the factory is very large, then we can assume independence. Okay, so that is just one scenario and one way of thinking about that independence assumption. Now, I will hasten to add that you will never need to reproduce this argument. But I'm putting it out there because, well, basically I respect your intelligence and I respect your curiosity. Some of you are going to want to know why. And so hopefully this gives you a little bit of clarity with respect to this independence assumption, at least in this particular scenario. Okay, so let's move on. So what is the last condition? The expected self-frequency condition. There, we need to see that the expected count is 5 or more for all the observations. So here, if the null hypothesis is true, in a sample of size 74, we expect 25% of them on average to be of each kind, and 25% of 74 turns out to be 18.5. And so you can see that the expectation for each of these categories, it's 18.5. They're all 5 or more, and so that condition is satisfied. Okay, good. Next question. Let's suppose we calculated our chi-squared statistic. And we found that our p-value for that test statistic is 0.019. The question is, what would be the conclusion if no level of significance was given? So there I paused. Did you come up with an answer on your own? One thing that I was asked to emphasize, and this was asked of me by the lab instructors, and that is to emphasize that when it comes to the significance of your test, when you're saying something about the significance, you cannot say anything if no level of significance is indicated. Right, so when no level of significance is given, we cannot say anything about the significance of the test. In other words, whether we reject the null. But we can still say something about the strength of the test. And so what do we mean by strength? That's when we look at the p-value and go to the table of adjectives. And we pick the most appropriate adjective. And so in this case, let's see, did I make an answer to this one? I meant to put in one more slide. You know what, if you bear with me for a moment, let me have a look at that. I think I meant to put in one slide here. Right, what am I going to say about the strength? Let's see. Oh, there it is. Is that it? Yeah, let's just move this up. Did I forget to erase the slide? No, I think we're good. Okay, so I'm just going to copy this slide and bring it up here. Yeah. I have to say, it takes a lot of work to make a lecture into a video. And as you can see, it's kind of easy to miss things. Right, so what I wanted to say here is we can say something about the strength of the test based on the p-value. Our p-value is 0.019, and so we go to the table. And we see 0.019, it's more than 1%, but less than 5%. So we can say that the strength of the evidence against the null hypothesis is moderate. Okay, so next question. Assuming the p-value of the test is still 0.019, what conclusions can you make at the 5% level of significance? So write a conclusion. I hope you paused and tried to write a conclusion. Here's what I got. We would reject the null at the 5% level of significance because the p-value, 0.019, is less than 0.05. We could then conclude at the 5% level of significance that the population distribution is not consistent with the assumption that the 4 kinds of truffles are distributed in equal proportions. Right, so we rejected the null. The null says equal proportions. We rejected it, so we're saying not equal proportions. And more specifically, we can conclude that at least one of those 4 proportions is different than 0.25. Assuming the p-value of the test is still 0.019, what would the conclusion be if the level of significance was 1%? Write down a conclusion. Well, what did you write? We would fail to reject the null hypothesis at the 1% level of significance because the p-value is greater than 0.01. Right? That's all there is to it. And what can we say in the end? We can just say that, well, our data, our observations from that one box of chocolates is consistent with the null hypothesis that the factory produces these chocolates in equal proportions. So we have no grounds to think that's not the case. And I think this might be the last question here for this scenario. Assuming the p-value of the test is still 0.019, what is the strength of the evidence against the null? Yeah, so we just actually did this. I guess that's, well, anyways, whatever. Assuming the p-value of the test is still 0.019, there is moderate evidence against the null hypothesis that the 4 kinds of truffles are distributed in equal proportions. And again, we have this diagram showing, yes, indeed, moderate evidence. Okay, so I hope that was helpful. And remember then, you're going to see a goodness of fit test on the midterm. Now, this example doesn't cover everything you need to know. You're also going to need to know how to calculate expected values and how to calculate contributions to the chi-squared statistic. If you want practice in that kind of calculation, you can go to the Moodle and find the midterm review material that I posted. Okay, so about the midterm. Just a reminder, that midterm is going to be written in class on February 27th. You cannot miss the midterm. If you have something going on that day, change your plans, come in and write your midterm. Look, I know there's probably about 20% of you who typically don't even come to class. I'm not judging you, that's your prerogative. I think it's better you come to class and I would be happy to see you. But I know some of you don't, for whatever reason. This is the one class you must attend, right? You have to be there for the midterm. The only exception would be people who have accommodations and they would have already arranged a separate place and a separate time to write their midterm. So do not miss it. If you miss it, nothing I'm going to do about it, right? So please be there. What's on the midterm? Central limit theorem is going to be there. So, basically you might be given a scenario. Does the central limit theorem apply in this scenario? Can we use the central limit theorem to assume a normal distribution or to assume a t-distribution, depending on whether the population standard deviation is given or not? So that kind of thing. And then there's the t-test. We have the one sample, two sample, and paired t-test, as well as the confidence intervals for each of those scenarios. So that's more the technical part. And then finally, there's going to be a goodness of fit test. So not too much stuff. I think this is going to be manageable. If you've been keeping up with the skill checks and you've been reviewing the lecture slides and attending class, asking questions, then you should be well prepared. The last thing you can do to get ready over this reading week is to, again, go into Moodle, find the document I posted, midterm review questions, work on those questions, maybe spend some time each day. By the end of the week, there's going to be video solutions. Maybe I'll do this as soon as I can, but at the latest, it's going to be at the end of next week. So by Friday at the latest, hopefully sooner. And that will allow you to just check your work and make sure that, that you got everything correct, or to fill in any gaps if there's things you didn't understand. Right, so yeah, so this is kind of apropos here. Let's talk about the homework, the tasks I want you to accomplish between now and the next time I see you, which is going to be Tuesday, February 25th. So first, review this week's slides. So that basically means review Tuesday's slides, because if you're watching this video, you're already reviewing Thursday's slides. Quiz 2 review. I've posted in Moodle Collaborate a short review of quiz number 2. So if you didn't get 100% and you want to know where you went wrong, have a look at that. Continue reading Module 5, that's the inferences for regression. Remember that in baby lecture number 3, that's where I introduced inferences for regression. If you haven't seen that lecture yet, then make time, watch it as soon as you can. Your MyLab homework number 4, I've been extending the due date for that. I finally extended that due date to be Monday, February 17, which happens to be tomorrow because today is Sunday. So that's on chi-square tests. Make sure you get that done on time so that you get it out of the way, and so that you can, for your statistics studying over the next week, you can concentrate on preparation for the midterm. And this is just a heads up that the next lab, the one that you will do when you come back, the next statistics lab, it's going to be on chapter 22 again. I think the last one was also chapter 22 on the chi-square tests. So that's coming up. And finally, there's the midterm review questions in Moodle. So as I said, solutions for the midterm review questions will be posted on our YouTube channel sometime over the reading week. I'll let you know. I'm going to send, when it's posted, I'm going to send you a link to that video. It's going to take probably a couple of days to make it. It's actually quite labor intensive. So, but in between taking care of the baby and taking care of Emma and doing housework and everything else I have to do, I will get it done. Probably by Wednesday. Let's say for Wednesday. Anyway, I'll send you a link when that's ready. So let's move on now to linear regression, some of the examples. So we're going to do 2 sort of big examples and at the end 1 little example. to go over all the concepts, all the new concepts related to linear regression. Now, before I do that, I just want to check that my microphone is on. I see that, yeah, this is responding, so yeah, it's on. Yeah, for a minute there, I had the fear that maybe I forgot to switch it on. Ha. Okay, so here we're going to look at a pretend study. It's going to be looking at the length of a snake as predicted by the mass of the snake. So you might be wondering where this data came from. Well, I just made it up. So it's simulated data. The scenario is as follows. We can imagine that some biologists, for some reason, for some biological reason, are interested in the distribution of the length of snakes, grass snakes in particular, in the island of Madagascar. Now, here's the problem for the biologist. It's not easy to measure how long a snake is, because if you catch a snake and you want to measure the length, well, the snake is not going to cooperate. One person has to hold the tail, another person holds the head. They stretch the snake out. Two more people might come up with a measuring tape to see how long the snake is. They write the number down. It's not a very easy procedure. So what would be easy is if we could just take the mass of a snake, which is easy to measure. We just throw the snake in a bag and we put it on a scale. We can easily measure the mass. If there was a relationship between mass and length, then we could collect data on mass and use that to estimate or approximate the data on length. So that's the big idea. And so here we have our data cloud. So you might first ask yourself, what can we see in this data cloud? What can we see in this scatter plot, if you will? And hopefully what you're thinking is two things. Number one, there seems to be a positive trend. But number two, there's a lot of scatter, so the positive trend is not very strong. Seeing that there is a positive trend, at least it looks as if there is, that justifies trying linear regression to see if a linear regression model works. So we could go ahead and try linear regression. Now here it is. This is from Minitab. This is a result of a linear regression. And I want to just ask you, see if you remember, based on baby lecture number 3, what this red line is. If I was to ask you, what would you call this red line? What would you say? And there's more than one right answer, by the way. So some of you might have said, oh, that is the regression line. That's correct. Some of you might have said that's the line of best fit. That's also correct. But now, thinking about what we learned in baby lecture number 3, we can say something a little bit more specific. We can say that the red line is an estimate of the population mean response. So remember, when we calculate this line of best fit, we get a y hat. This equation with y hat has two model coefficients, b0 and b1. b0 is an estimate of a slope, of an intercept. b1 is a slope. Behind sort of the scenes, in the sort of population at large, we actually have population values for both of these things. So in other words, b0 and b1, they come from a sample. b0 and b1 are random variables because every time you take a new sample, you're going to get different estimates. b0 and b1 will be different. Those are random variables. Beta 0 and beta 1 are not random. They are population parameters. So they have exact values. We don't know what they are, but they have exact values. So the red line is an estimate of a population mean response, is the way we say it. So that mu with a y in the bottom corner represents a population mean response for a given value of x, x being the predictor. So that's the red line. Now what about that green line? Those two green lines. Do you remember what those represent? So what we call that, those two green lines, we say that represents a 95% confidence envelope. So that gives us a measure of uncertainty. And again, why do we have uncertainty? Well, this red line itself, this line of best fit, you can kind of think of that as a random variable too. Every time you get new data, that line of best fit is going to be a little bit different. This confidence envelope gives us a measure of the uncertainty. So the green line marks a 95% confidence envelope for the population mean response. Now let's look at something a little more a bit more concrete. So suppose we are interested for some reason in the population mean length of grass snakes with a mass of 2 kilograms. So that red dot that just bounced in, let me just bounce that in again. That red dot represents an estimate of the population mean length for grass snakes who are 2 kilograms in mass. That's a point estimate. Now what we have learned is that a point estimate is not sufficient, because with a point estimate alone, we have no idea of how much uncertainty there is in that estimate. And after all, statistics is all about quantifying and accounting for uncertainty. So how do we account for uncertainty here? Well, on this graph, we have an upper and lower bound for a 95% confidence interval for that population mean response. And here we can read this off the graph. If you look on the vertical axis, the upper bound looks like around 200 centimeters in length. The lower bound is something a little bit above 100. So let's say 120 to 200 centimeters in length. This is a 95% confidence interval for a population mean response. What it means is for the population of all grass snakes who weigh 2 kilograms, this is a confidence interval for the population mean length of those snakes. So that's how you read it. Now, I should add that these green dashed lines, you will not learn how to calculate where they go. Right, so these confidence intervals, we're just going to either read them off of graphs, or in some cases we're going to be given actually the upper and lower bounds of the interval for specific values of the predictor variable. So you don't need to worry about calculating that. What we will calculate will be a confidence interval for the population mean slope. Sorry, I didn't mean to say mean. For the population slope. Which symbol on this slide represents the population slope? You should have said beta 1. Beta 1 represents the population slope. So we will be calculating confidence intervals for the population slope, but you will not be calculating confidence intervals for population mean responses, which means the green dashed lines. That's a complicated calculation, and we don't expect you to do that. Okay, so what are we looking at now? This is typical Minitab output. You're going to see lots of these probably through this course. There's a few of the plots that matter the most. In fact, the top 2 plots are the ones that matter the most. So what are we looking at? Well, all of these plots are for the residual errors. So remember, a residual error will be the difference between an observed value and its corresponding fitted value. If we just go back a slide. So for example, I'm not sure how big the pointer is here. I made it as big as I could, but sometimes when I record it gets small again. But if you look carefully, there's a yellow pointer. Let's look at, let's hear this one. So here's an observation. If we go straight down from that observation to the line of best fit, that would give us the corresponding fitted value, and the distance between those is the residual error, right? So the residuals are kind of they're associated with the scatter in the scatter plot, the scatter about the line of best fit, and they're an expression of individual differences. You can think of them as due to individual differences. So back to this. So what we're seeing here, these blue markers are all represent, these blue markers are the residual errors. And so we had, 50 data points? And so there's 50 residual errors. Now, this first plot on the top left is a normal probability plot. Now, for some of you, you're going to look at this and think, oh, there's a red line. So does that mean this is a regression? It's not regression. This plot is not regression. This is a normal probability plot, and it can be used for only one thing. That is to ascertain whether the data in the plot is consistent in distribution with a normal distribution. So here, the data in the plot are the residuals. We're asking whether the residuals are consistent with a normal distribution. And how can you tell whether that's the case? Well, if these blue markers look kind of like beads on the red string, then you're good. Then we can say that the distribution of those residuals is approximately normal. And what do I mean by beads on a string? What I really mean is these markers, these blue markers, should be in an approximate straight line. Here they are in an approximate straight line, so we're good. So we can say that the residuals are approximately normal distribution. Now, if you look below at the histogram, you can see the histogram is consistent with that because that histogram is unimodal and it's roughly symmetrical. Of course, we don't expect a perfect bell curve in the histogram with only 50 data points. But what we have there is a pretty good representation of a unimodal symmetrical distribution. Right, so that's that part. Now, the other graph that's really of relevance is the versus fits plot. That's top to the right. In this graph, we need to see two things. So these, again, are residuals. The residuals are plotted on the vertical axis versus the fitted values, the y-hats, on the horizontal axis. We need to see two things. First, we need to see that there's no trend in the residuals. In other words, think of it this way. If you were to put a line of best fit, a regression line, through these residuals, that regression line should be the x-axis at 0. It should be the horizontal axis. So here you can kind of see that's the case. Secondly, you need to see that the spread in the vertical direction is roughly constant as you move from left to right. And here that is also the case. And so that condition is satisfied. And by the way, if you want to see examples of residual plots where these conditions are not satisfied, then I'm pretty sure in baby lecture number 3 you're going to see some examples, possibly in baby lecture number 2 as well. So it's worth having a look at those. And by the way, you don't need to look at the video. You can also just go to the Moodle and download the slides themselves. And then you can do it very quickly. Look through the slides and you'll see examples. So now, what was that last slide all about? We want to know whether a linear regression model is appropriate for this data. And so in order for that to be the case, there are certain conditions that need to be satisfied. And so here are the most important ones. First, as I mentioned, the residuals must be approximately normal in distribution. We can call this the normality condition. And it's checked by looking at a normal probability plot of the residuals, as we just did. There's the scatter plot, must also suggest a linear association. So in order for the linear model to be appropriate, when we look at the actual data, the x values versus the y values, that scatter plot, it should look like there's a linear trend. And that's what we did at the very beginning. I showed you the scatter plot and I asked you, does it appear that there's a linear trend there? Yeah, it does. So this is called the linear enough condition. Now here's the trick. The linear enough condition is typically assessed not by looking at the scatter plot of the original data, but by looking at a scatter plot of the residuals. This linear enough condition is satisfied if there is no trend in the residuals, right? So going back a slide, that linear enough condition is tested by looking at the versus fit plot. This is in the top right-hand corner of this slide. And it's assessed by checking whether there's no trend in that data cloud, in that scatter plot. You can see here there is no trend. Right now, the reason I'm emphasizing this is because often students get confused, and when they are asked whether the linear enough condition is satisfied, they look at the normal probability plot and they say, yeah, those data points are in a straight line, so the linear enough condition is satisfied. That is not the linear enough condition. You look at the normal probability plot to test what? To test to see if the residuals are approximately normal in distribution. That's all we can do with the normal probability plot. The linear enough condition is tested by looking at the versus fits plot. So make sure you remember that. And in fact, it's written right here, I think. Look, if we go here. Yeah, no trend in the residuals. We look at the residuals versus fitted values plot. We want to see no trends. That's the second condition. The third one is something you're going to remember from 2208. The spread of the y values must be roughly the same for all x values. Now, this condition, we could check it by looking at the original data, but again, it's more correctly checked by looking at the residuals. I call this the constant spread condition. In the lab, they probably call it the thickening of the plot condition. right? So if you want to just see that terminology, again, look back at the slides for the baby lecture number 3 and also baby lecture number 2. It's probably there as well. So in the lab, they might call this the thickening of the plot condition. The point is, you don't want to see a thickening of the plot. You don't want to see that. And in other words, you don't want to see any change in the spread. So if you just go back one more time to emphasize, here in the versus fit plot, we can see in those residuals, the spread in the vertical direction is roughly constant. That's what we need to see. So we have that. And finally, we must have no unusual observations, which include observations with large residuals or leverage points that are potentially influential. Now, what mystery is this leverage points and potentially influential? You might not recall what that's all about. So I decided to throw in a few extra slides to discuss that. So first, let's talk about large residuals. That's kind of obvious. But let's look at it again anyway. So if you look at these two plots, look at the scatter plot on top. Can you see the data point that has the biggest residual? Just identify that sort of in your mind's eye. I'll give you a second to do that. The data point here with the largest residual is this one, right? Because look how far away that observation is from the line of best fit. It's a really, really big distance away. That is a large residual. So because of a large residual, the coefficient of determination isn't that big. It's fairly small, 62%. What happens if we remove that residual? Well, we'll see that in a minute. Let's just look at the equation. Yeah, here's the line of best fit. We have an intercept of 90 and a slope of 36. So question now is, what happens when this data point with the large residual, if we just throw it out? And so look at the scatter plot on the bottom. That's the same data, but that data point with the big residual is removed. What do you think is going to happen to the coefficient of determination? Is it going to get bigger or is it going to get smaller? So hopefully you realized the coefficient of determination is going to get bigger. Why is it going to get bigger? Because there's less scatter. So one thing to remember as a sort of a rule of thumb, if you will, is that the less scatter there is about the line of best fit, the bigger will be the coefficient of determination. Right, so here, when this data point is removed, the coefficient of determination gets bigger. In other words, the quality of the fit gets bigger, the quality of the model gets better. And so here it gets quite a bit bigger. Now it becomes 85%. What do you think is going to happen to the slope? Well, in this case, the slope hardly changes at all, just by a very tiny amount. And so we say that this observation, the one that we removed, has little influence on the slope because the slope does not change when it's removed. So this is what we mean by influence. There are cases where one single data point can have a really big influence on the slope of your line of best fit. This is not one of those cases. This observation with a big residual has essentially no influence. So we do not call it an influential point. Okay, so now let's go on to the leverage points. What is a leverage point? Look at the plot on top, and in your mind's eye, pick out the data point that is a leverage point. So that one is the leverage point. What is the definition of a leverage point? It's an observation that is far away from the rest of the data in the horizontal or the x direction. And just notice something in this first plot. Look at the line of best fit and look at all of the observations apart from that leverage point. Is that line of best fit a good representation of all those green circles on the left? Well, you should realize that it's not, because if you were to just by hand draw a line of best fit, you would want it to pass through those green dots that you see on the left. You see what this leverage point is doing? It's giving you this sort of wonky best fit where the red line, its slope has been pulled toward that leverage point. And so we're getting a bad fit. Well, how bad is the fit? The R squared is terrible. And remember too, see that leverage point has a very big residual. The line of best fit has a slope of only 11, in this case centimeters per kilogram. What happens when we remove that leverage point? What do you think is going to happen to the coefficient of determination, the R squared? Bigger or smaller? What do you think is going to happen to the slope when we remove that leverage point? Well, there's what the R squared becomes. It's increased by a lot. In the plot on the bottom, you can see that we have a fairly small amount of scatter around the line of best fit. That's consistent with a fairly large coefficient of determination. So R squared increases, and why does it increase? Because we've removed that leverage point, which also had a very big residual. Now what about the slope? It's kind of hard to see by looking at the graphs, but the new slope is more than 3 times bigger than the old one. And so we say that this leverage point is highly influential. So this leverage point is also an influential point. Why? Because when we take it out, the slope changes by a lot. Okay, so all of these, these last 2 slides, all of this stuff is a review from 2208, but I'm sure most of you kind of forgot this stuff. So here it is again. Now you know. Moving forward, oh yeah, I forgot I had one more example. Which is the leverage point in this case? Just in your mind's eye, identify the leverage point. So there it is. Why is this a leverage point? It is far away from the rest of the data in the x direction. But notice the residual for this leverage point is very small. Furthermore, this leverage point is consistent with the linear trend you see in the rest of the data. And so this is an example of a leverage point that has no influence, right? So on the bottom plot, we've removed the leverage point. And if we compare the R squareds and the slopes, you see there's no change. So this is a leverage point, but it is not influential. Okay, so there's the full sort of spectrum of possibilities for your pleasure. So let's move on now. Here I'm trying to remember what point I was going to make next. So this is again our snake data. We have our line of best fit in red. We have our 95% confidence interval in green. Now I recall. So let's look at some more Minitab output. Typically, you'll be given a table like this. And so you have in the middle a column for the model coefficients. So here's a question I'm going to ask you. This time I want you to pause and try to answer the question. Some of you are going to be able to do that. Some of you may have to look at your notes. See how you do. Question is, what is the estimate of the population mean length of grass snakes that are 8 kilograms in mass? What is our estimate? So pause the video now and just take a few minutes to try to figure that out. Okay, so when faced with this kind of problem, there's 2 steps you have to make. First, you need to write down the equation for the line of best fit, for that red regression line. And how do you do that? Well, you see in the table, you have the coefficients. The number on top, it's called the constant. That is the y-intercept. That should be 0. The number below it, it's called mass. Mass is the name of the x variable, the predictor. The number corresponding to mass, that number 10.89, is b1, that's the slope. And so you can use those to construct an equation for your line of best fit. Now, if we're interested in making a prediction or getting a fitted value for snakes of 8 kilograms in mass, we just need to replace x with 8 kilograms. So looking at 8 kilograms, what we're going to do is figure out what the corresponding y value is. And so how do you do that? Well, you plug in 8 where you see x, you multiply that by the slope, and then you add the intercept, and you get a value. Right. So this kind of calculation is very simple. It's basic arithmetic. But if you forget how to do it, it's impossible. Right? So make sure you get some practice with this. I'm going to give you another one later in this video. Make sure you give it a crack and practice it a little bit. so that when you get to the midterm, if you're asked a question like this, okay, take that back. This midterm will have no regression. When you get to the final and you get a question about regression, you're asked to calculate a fitted value or a predicted value. This is how you do it, starting with the table that gives you coefficients. Okay, next question. This is a question you should be able to answer as long as you've seen the baby lecture number 3. Question will be to calculate the coefficient of determination and also the correlation coefficient, and think about what these numbers represent. How, if you were to explain to somebody what the numbers represent, what would you say? Pause the video now and give this a crack. This is going to take probably 5 or 10 minutes, so give yourself some time to do this calculation. I'm back. I noticed that I've been talking faster and faster as this video goes on. Yeah, let me try to slow down a little bit. Those of you who've come here from other parts of the world, you might notice that Nova Scotians, well, we tend to talk really fast, my son, and I do apologize for that. I'll do my best to slow down a little bit because I want to be understood. Let's get back to the question. Coefficient of determination, that's the R squared. The R squared is the proportion of variation in the response in the Y values that is explained by differences in the predictor of the X values. So what's the total variation in the Y values? It's the sum of squared total. So that's the 346,363. What proportion of that is being explained by this model? Another way of saying it is what proportion of that total variation is being captured by the fitted values? Or you could say what proportion of the total variation is systematic? That's the regression one. That's the sum of squares of regression. It's also called the sum of squares of Y hat. That's the 47,699. So if you take that ratio, you could multiply by 100 if you want. You get 13.77%. Starting from here, how do you get the correlation coefficient? You simply take the square root of that value. That gives the correlation coefficient, and this provides a measure of the strength of the linear association between the response Y and the predictor X. Notice the correlation is very small. The coefficient of determination is also fairly small. Why are these numbers so small? Because if you go back to the scatter plot, you can see that there's a lot of scatter in the data. So we have a low correlation and a low coefficient of determination. So that makes sense. Those values make sense. Okay, now the final part of this example is to do the inferences. And we have two sides of that inferential coin. We can make a confidence interval or we can conduct a hypothesis test. The good news is, in the context of regression, the inferences are very easy. So first, let's suppose we're going to construct a 95% confidence interval. And also we're going to conduct a 5% two-tailed test. In both cases, we use the same critical value. So here, because the sample size is 50, the degrees of freedom in a regression scenario like this one is the sample size minus 2. Essentially, it's the sample size minus the number of model coefficients. And we have two model coefficients. We have B0 and B1. So in this case, the degrees of freedom is 48. We can estimate our critical values using 45 degrees of freedom. So for 95% confidence interval or for a 5% two-tailed test, we get a critical value of 2.014. So given that, let's construct a 95% confidence interval for the population slope. And then we'll do the interpretation thing. So what I'll do, just to get you started, how do we calculate this interval? It's always the same. We have a point estimate, that's B1, that's a model coefficient, plus or minus a critical value multiplied by the standard error. So you can pause here, take a few minutes and do this calculation, get the upper and lower bound for this interval. Right, so the good news here is you can read values right from the table. You see that B1, our estimate of the population slope, is given by the coefficient 10.89. Then we go plus or minus, we have a critical value, we just looked that up, and multiply by the standard error. I just noticed a typo. This is supposed to say B1. How absurd. What a dumb mistake to make. Yeah, so as I was saying, the standard error for that point estimate is given in the table. It's called the SE coefficient. It's 3.93. So this point is the standard error is given. You don't have to calculate the standard error like you do when you do, let's say, a one sample t-test or a two sample t-test. So that makes the calculation a little bit more straightforward. So here is our confidence interval. Now the interpretation is important because it's a little bit different. Here I'm including units because that's the context. And so here's what we're saying. First, the conditions, assuming the conditions for regression and for the central limit theorem are both satisfied. Here we're 95% confident that the population slope, that beta 1, is between 2.98 and 18.81 centimeters per kilogram. Since the interval is positive, we have evidence at the 95% confidence level that there is a positive association between the predictor and response variables, meaning that the population slope, the beta 1, for the linear association between the predictor, that's snake mass, and the response, that's snake length, that beta 1 is plausibly greater than 0. So that's an example of the kind of interpretation that I want to see. Now, I should add that in the lab, it might be that they expect to see something slightly different. You need to make sure you know what they want in the lab. But in the end, what really matters is what I want, because I'm marking your midterm, I'm marking your final, and those two things together are worth a lot more than the lab, right? So just heads up, sometimes in the lab, they expect slightly different things. And I'm going to depend on you to figure out what that is by talking to your lab instructor. Okay, so we looked at one side of the inferential coin, the confidence interval. Let's look at the other side. Here, we're going to look at a hypothesis test. The null hypothesis in this scenario is always the population slope is 0. If the population slope is 0, that tells us that there is no association between the predictor and response. If there is an association between predictor and response, then we would have evidence that the population slope is not 0. So a not 0 is the default alternative hypothesis in Minitab. And typically it's the one that we use. We want to know if there is a linear association between predictor and response. We can say that there is an association if we have evidence that the population slope is not 0. So here I'm going to ask you, this is based on what was explained in baby lecture number 3. Pick out from the table the test statistic and the p-value for this hypothesis test. Just take a moment and do that, like, in your mind's eye. So you should be looking at these two numbers, right? So the second row, that's the row that corresponds to the slope. Our best estimate for the population slope is the 10.89. That's B1. We have our measure of uncertainty, the coefficient, standard error of the coefficient, 3.93. And there's your test statistic and there's your p-value. So you can see, you can read them from the table. If they give you the whole table, you can just read them. Can you show how the test statistic is actually calculated for this hypothesis test? Take a moment to do that. So here it's quite easy. And remember that the way we calculate test statistics when it's a t-test, it's always the same. We compare what we observed, and that's B1, with what we would see on average if the null was true. and that is, in this case, it's 0. And then we divide by our measure of uncertainty, the standard error of B1. And so that's where the 2.77 comes from. So see, it's quite easy if you're given the table. It's a very simple bit of arithmetic to do the calculation. Okay, now this slide, I kind of forget what I was going to say here. Let's see. Yeah, I think I meant to, well, I'll show you what I meant to do. I got distracted when the baby started crying. Let me just use that as an excuse. I meant to put some animations on this slide. Okay, so you can pretend you didn't see that. So if you were asked, if you're given this table and asked about the significance and strength of the test, you just need to remember that significance refers to whether or not you reject the null hypothesis, and so you compare the p-value with the level of significance. And here it's a 5% test, right? So we got that. And then the strength of the test is evaluated by just comparing the p-value with the table that we have for adjectives for the strength of the evidence against the null. And so here we can say for significance, we can reject the null because the p-value is less than 0.05. And we can therefore conclude that the population mean slope is not 0, meaning that there is a linear association between snake mass and snake length at the 5% level of significance. There's a perfect answer. For strength, we merely need to observe that the evidence against the null hypothesis is strong, and we know strong because, well, there it is. The p-value was 0.008. It's between 1 part in 1,000 and 1 part in 100. It's in this row. So yada yada. Okay, so that was the first example. Now, if you want, here you could pause the video, maybe take a little break, and come back and finish this this video. You could also pause it and come back another time. I'm actually going to take a break right now, although you won't really notice because I'm going to edit that part out. But yeah, I'm going to take a break right here, and I'll see you on the other side. Hi everybody, I'm back. So let's see, we just did a linear regression. Let's do one more. And in this case, you'll have a chance to practice all those same calculations again. Here we're going to look at the mean longevity for a US state versus the mean illiteracy rate in that state. And this is actually real data. So here we have for the 50 states in the US. On the horizontal axis, we have the percent of the adults in the population who are illiterate. So that's ranging between 0.5% up to 3%. And on the vertical axis, we have the mean life expectancy in years for people in that state. And so what's the first thing we need to look for in our scatter plot? Well, hopefully you're thinking, we need to look to see if it looks like there's a linear trend in the data. And here it kind of does. It looks like there's a sort of a negative association such that the greater the illiteracy rate, the lower the life expectancy. And so just based on that, we're justified to try a linear regression. We'll still have to check conditions by looking at residuals afterwards. Right, so what's that red line called again? That's your line of best fit. That's your regression line. It's also our estimate of the population mean response. Let's look at one particular value. So let's suppose we're going to consider the adults, we're going to consider the states for which the illiteracy rate is 2.0%. And we want to know what the population mean response is for such states. In that case, we want to know what the life expectancy would be for states where literacy rate is 2%. And so how do we make that estimate? How do we estimate the population mean response? In other words, wait a sec, I'll take a sip of tea. How do we estimate the population mean response? We do so with an interval estimate. So maybe just take a moment, look at that plot. just write down what you think the upper and lower bound would be for this interval. So looking at this plot, it looks like we have bounds starting just above 69 years expectancy, 69.2 I would estimate. As the lower bound, the upper bound is at just above 70, so I estimated that to be about 70.3. So this is our 95% confidence interval that we're reading from the graph using that green dashed line, that confidence envelope. Anything unusual about the data here? Anything that looks problematic, I would say? You might notice we have a couple of kind of unusual values here. So in the lower left-hand corner, we have a state where the illiteracy rate is just about 0.5%, but it has a much lower life expectancy than what you would expect based on the rest of the data. And then in the sort of center top, we have a state where the illiteracy rate is nearly 2%, but that's also the state that has the greatest life expectancy. So what's going on there? I don't know. It's probably interesting. Nevertheless, it's a good idea in situations like this to leave such data points aside and to run an analysis on what's left over, right? Because we don't want data points with very large residuals to spoil the rest of our analysis. And just to emphasize the point, if we go to check our conditions, remember the normal probability plot in the top left. We use that to ascertain whether the residuals are approximately normal distribution. And here you can see that in the tails, we got some weird things going on. We have some deviations from a straight line. And also we have a couple of points, one on the left, one on the right, that look really unusual. Looking at the histogram, we can see also very clearly that we have one outlier on the far left and one outlier on the far right. The versus fit plots in the top right-hand side, we can kind of see the same thing. We can see those two data points, and also in the versus order. So what we're looking at, these two data points appear in all four of the graphs. They are substantially unusual, and so we would be justified to take those out and then conduct the analysis without them. So instead of analyzing 50 states, we're going to analyze 48. So here's the data with those ones. We're going to take them out. And here's the question for you. Right, here's the first question. If we remove these two data points, how will that impact the coefficient of determination? And how will it impact the width of our 95% confidence envelope? Now's a good time to pause and think about it. Just think about the answer to these questions. Right, so removing those large residuals, and why do I say large residuals? Again, because these two data points have very big residuals. The distance from the observation to the line of best fit in both cases is very large. So if we take those out, we're going to be reducing the sum of squares attributed to individual differences, the sum of squared of errors. And therefore, this will increase the coefficient of determination. And so just to remind you, the total sum of squares for your observations, your y values, is partitioned when you do a regression. It's partitioned. Some of it goes to a systematic component of variation. That's your sum of squares of y hat. And the rest goes into a random component of variation due to individual differences. That's your sum of square of error. And so if we make the sum of square error smaller, then the proportion of variation accounted for by the y hats is going to be correspondingly larger. So in other words, removing those two data points and reducing the variation due to individual differences, that's going to increase the proportion of total variation due to a systematic change, the systematic component of variation, the y hats, which is what our r squared is. Just noticing something, probably I should include here times 100%, because usually r squared is reported not as a decimal, but as as a percentage. So let me just throw that in there. Times 100%. Okay, that looks better. All right, so let me say this another way. Again, as I mentioned previously in the previous example, R squared is big when scatter is small. If you remove those two data points, with each of which has a very large residual, removing them reduces the scatter, and that then increases the R squared. R squared moves closer to 100%. And so then I also ask, what's going to happen to the confidence interval? Well, if you're reducing the sum of squares due to errors, in other words, the variation due to individual differences, if you're removing some of that, that reduces the uncertainty. And if uncertainty gets reduced, the confidence intervals become less wide. And so this confidence envelope will become narrower than before after removing those two data points with large residuals. So R squared will get a little bit bigger, and the 95% confidence interval will get a little less wide because we've removed the two largest residuals. Where might you see this concept, say, in a final exam? You could well see it in like a multiple choice question. They might ask you exactly what I asked here. They might ask, here's an example with some data. We're going to remove that one data point with the biggest residual. How might this impact R squared? How might this impact the width of the confidence envelope? And then you'll have some options to choose from. So just a heads up on that. So now that we removed those two data points, you can see that our residuals look quite a bit better. So in the normal probability plot, most of those data points are lined up like beads on a string, and so we can say that the residuals are approximately normal in distribution. If you look at the versus fits plot, you can see there's no trend in the residuals, and also the spread of the residuals in the vertical direction is roughly the same as you move from left to right. So we're all good with our conditions, so we can continue with the regression analysis. So here what I'm going to ask, what is the estimate of the population mean life expectancy when 2% of the adult population is illiterate, based on the values in this table? Remember, first you have to write down the equation for the line of best fit based on what you see in the table, and then you have to make a substitution and calculate. Pause the video now and do that calculation. So we remember that the table gives us our model coefficients. The first one called constant, that's the intercept, that's your B0. The second one, in this case, is called illiteracy. Illiteracy is the name of the predictor variable. That coefficient gives us the slope, that's B1. And so we can write down the line of best fit, the equation for the line of best fit. And now if we want to estimate the population mean life expectancy when 2% of the adult population is illiterate, then x is equal to 2%, or 2. It's just equal to 2. So we put 2 in there, and we get a population mean life expectancy of 69.566 years. Next question. Here, calculate the coefficient of determination and the correlation coefficient, and explain what these numbers represent. Take a few minutes, pause the video, write down your answers for these questions. So the coefficient of determination, we make a ratio. It's the ratio of, on the bottom, the total variation in your observations in the y values. On top is the proportion of that variation that's accounted for by the y-hats, in other words, by the regression line. So it's the sum of squares of regression on top, also called the sum of squares of y-hat, divided by the sum of squares total. And then you can multiply by 100% if you want to make a percentage. So here we get 0.5392, or 53.92% if you will. This represents the proportion of variation in the response, y, that is explained by differences in the predictor x. How do we get the correlation? We just take a square root. So here the correlation coefficient 0.7343. This provides a measure of the strength of the linear association between the response y and the predictor x. Next, we're going to look up a critical value so that we can then make a 95% confidence interval for the population mean, I almost said it wrong. We're looking for a 95% confidence interval for the population slope, the beta 1. And then we'll also conduct a two-tailed hypothesis test. So we'll do the confidence interval at 95%. The two-tailed test will be at 5%. What are the critical values? Just in your mind's eye, pick out the critical value in this case. Notice that the degrees of freedom is 46. It's the size of the data set. So we have 48 data points, 48 states now, minus 2. And the reason we go minus 2 is because our model has two coefficients, B0 and B1. So with the degrees of freedom 46, we can estimate using 45 degrees of freedom, 95% interval, or a 5% two-tailed test. The critical value, again, 2.014. Make a note of that because you're going to need it in a minute. Just write that number down. So for the confidence interval, construct a 95% confidence interval for the population slope beta 1 and then interpret your result. Oh, I just noticed I have the degrees of freedom here incorrect, so let me just fix that. Oh, geez, you're seeing the answer. Well, that wasn't very well planned. I bet if I go here again, you won't remember what the answer is. Let me just do that. Okay, go ahead and do the calculation. Chop, chop. Right, so confidence intervals always have the same form. It's a point estimate plus or minus a margin of error. The margin of error is just a critical value multiplied by standard error. Here again, I have B0. That's silly. That is silly. B1. That's supposed to be B1. There it is. Right, so here we can see our coefficients. So our best estimate for the slope, it's our B1. It's minus 1.557. Our critical value, 2.014. And the standard error for B1 is 0.212. Right, so these are read directly from the table. And so this calculation is quite straightforward. We get an upper and lower bound. How do we interpret this? So what I would say is, assuming the conditions for regression and for the central limit theorem are satisfied, we are 95% confident that the population slope is between minus 2.00 and minus 1.15 years per percent illiteracy. So what that means is for every 1% the illiteracy rate increases, we expect to see a decrease in the, what do we call that again? Suddenly I'm drawing a blank. In the longevity, right? A decrease in the longevity by somewhere between 2 years and 1.15 years. Now then we go on to say, since the interval is negative, we have evidence at the 95% confidence level that there is a negative association between the predictor and response variables, meaning that the population slope for the linear association between the predictor, illiteracy for a US state, and the response, mean longevity for such states in years, is plausibly less than zero. Is plausibly less than 0. Okay. Hypothesis test. The null is always the population slope is 0. The alternative is it's not 0. What is the test statistic at its p-value in this case? Just pick those out with your eye. Test statistic and p-value. So hopefully you're looking at these two numbers. Our test statistic minus 7.34. Our p-value is pretty much 0. Show how the test statistic is actually calculated. it's a t-test, and t-tests are always the same. You take what you observed, in this case, beta 1 minus 1.557, minus what you would expect to see if the null was true, in this case that's 0, and then divide it by our measure of uncertainty, which is given 0.212. And so that's where the minus 7.34 comes from. So testing at the 5% level of significance. I did it again. Well, I guess it doesn't really matter at this point, but my OCD won't let me not make a change here, so I'm going to make a change here if I can. Let's see. And I'm sure you can be patient with me. Let's see. Oh, look, I even forgot to put a full stop at the end of that sentence. So what do we have? So for significance, what do we want to write? We want to state whether or not we're going to reject the null and say something about why and what that implies. So here we could say, here we can reject the null because the p-value, which is essentially 0, is less than 0.05. We can therefore conclude that the population mean slope is not 0, meaning that there is a linear association between percent illiteracy, that was our predictor, and life expectancy, that was our response. And this at the 5% level of significance. Just like that. The strength of the relationship, 0.000, we got to say we have very strong evidence against the null hypothesis. Did I say the strength of the linear relationship? That is not what I meant. The strength of the linear relationship is what? It's called what again? It's called the coefficient. It's called it's called the correlation coefficient. What I meant here is to assess the strength of the evidence against the null. The strength of the evidence here, it's very strong. And how come I can say that? It's because of this. Okay. Sorry, I'm getting tongue-tied now and then. I'm operating on very little sleep, I must say. Not complaining, though. Okay, so that example was pretty fast. We have one more example. This one is quite short. It's only 4 or 5 slides at most. Here, you're not going to be doing calculations. I'm just going to tell you some other things about regression that you haven't seen yet. And so here, the scenario is we're going to look at the daily cost of heating a house as predicted by the daily mean temperature. So here's the data. This data is data I actually made up myself. On the horizontal axis, we have the daily mean temperature. So you see, it ranges between minus 10, which would be winter time, up until plus 15, which would be summertime. On the vertical axis, you have the daily mean heating cost. And so clearly there's a very strong negative linear relationship. Yeah, so the warmer it is outside, the less you're going to spend on heating. Now here's what I want to ask is, well, first of all, the red line here, you know what that is. That's your regression line. That line represents your best estimate of the population mean response at various levels for the predictor variable. The green envelope is just the 95% confidence interval, or confidence envelope for the population mean response. The purple line is something different. That's what's new here. So here, the green one is the interval for the population mean response. The purple line is a prediction interval, not called a confidence interval, but a prediction interval for an individual response. So the difference here is crucial. The first one, the green one, is for a population mean response. The purple one is for an individual response. And what do you notice? The intervals for the individual response, it's a lot wider. So why is that? Well, let's go back to the central limit theorem. So that was the case where we would say, if y is a quantitative random variable that follows any distribution, it has some mean, mu, and some standard deviation, sigma. And if y bar is a sample mean, computed from n independent and random observations of y, then y bar, that sample mean, is approximately normal in distribution. It's centered at the same place as the distribution for individual measurements, but its uncertainty or spread is smaller. So its uncertainty or spread, its standard deviation, it's sigma over root n. So for the individual measurement, the standard deviation is sigma. For the mean value, the standard deviation is less because we're dividing by that square root of n. And that reflects the idea that when you take an average, you have more information than you do if you look at one individual value. Now, what does this have to do with those purple dashed lines? The point is this: an individual measurement has more variation, or you could say uncertainty, than a mean value. Likewise, there's more uncertainty when estimating an individual response compared to estimating a population mean response. And so that's why, let's go up here again. That's why the confidence envelope in purple for individual responses is so much wider than the green confidence envelope for population mean responses. Okay, so now let's look at a few numbers. And this is something you're going to need to be able to do for the exam. You'll be given output like this, and you'll be asked questions about the CI, which is the confidence interval, and the PI, which is the prediction interval. So what do we see on top of this, this output? We see the equation for the regression line. It has an intercept, 10.151, and it has a slope, 0.3130. And so here, we're going to say, what if we set the daily mean temperature to 10 degrees? Setting that to 10 degrees, we can get a predicted value. How do you get that? Well, we have our equation for the line of best fit. We could plug in 10 and we would get a number. The number we would get is down here. See where it says prediction? The fitted value is 7.02. It's $7.02 cost as a daily mean cost, a daily heating cost. Now, associated with this value, we can construct a confidence interval for a population mean response when the temperature is 10, but we can also make a confidence interval for any individual response, right? So suppose we're in a city like Halifax. Suppose there are, well, let's say we take a few 100,000 houses. If you take all those homes and you take a day where the temperature is 10 degrees and take the average cost, that would be something like a population mean response. And we can make a confidence interval for that. But on the other hand, if you just pick one home at random and you want to predict how much the heating cost was for that one home when the temperature was 10 degrees, then that prediction has a bigger interval. So that's the point. So if we look at this first interval, this is a 95% confidence interval for the population mean response when the temperature is 10 degrees. And the other one is a 95% prediction interval for an individual response when the temperature is 10 degrees. And you should notice that the prediction interval is much wider than the confidence interval, right? The lower bound is smaller and the upper bound is bigger. So we're just about finished. Let's just look at a picture of that. So this is the same data, but we're zooming in at 10 degrees. So if we look at 10 degrees, our fitted value, the $7.02, our fitted value is right there. The 95% confidence interval for the population mean response is given by these two green dots. And the 95% prediction interval for any individual home is given by those purple dots. And you can see it's much, much wider, right? So the thing to remember is if you're predicting a mean response for a population, you're going to do so with a certain amount of uncertainty. That's going to be reflected in the width of your confidence interval. But if you're predicting an individual response, that confidence interval is going to be much wider, reflecting much greater uncertainty due to individual differences, right? Right. So a population mean response has less uncertainty than a predicted individual response. How about that? We are done. Good. So thank you for watching. What do I need to say now? I guess not much. You probably want to get on with your day. Well, I can't talk anymore. You probably want to get on with your day. If you have any questions about this, anything that you saw here in this video, you can leave a comment on YouTube. You can send me an email. Or if you want, you can wait until you see me when we come back after the reading week. Study hard. Don't forget to look at the midterm review material. Work on that over this next week. And keep an eye out for the email that I will send you with a link to the video solutions. And so that's all. So great. Bye-bye for now. Bye.